Yes, we are happy to have you here and looking forward to your talk.
Thank you. Well, thanks for inviting me over. I'm from the VU University Amsterdam Research Institute, Faculty of Human Movement Sciences. It's a long way to go. And I will talk about is stability an unstable concept, or more directly about quantifying dynamic stability of human locomotion. I won't go into details about the question if stability is an unstable concept, but I hope that between the lines of my talk you can read the answer to that. So, first of all, why am I interested in dynamic gauge stability? Well, it's mostly because of falling of theology. My grandma fell herself a few years ago, and she broke her hip, and then she fell again, broke the other hip. And my grandma did surprisingly well, but a lot of people do not so well after breaking a hip. So you would want to be able. Oh, wait a bit. To detect if people are prone to falling, so that you can subscribe them some intervention. For instance, say we give you one of those cars where you can walk behind, or we give you a fall training, or we give you hip protectors, or the fall airbags which the Japanese guys are making, something like that. This was, if you do this in a correct way and you're able to identify the people who need something like that, this will save you a lot of money. As you can see, this is the amount of money it costs in the Netherlands per year, 370 million euros per year. So this is a lot. So given that a lot of these falls occur during walking, I think it's quite obvious why I'm interested in this. So, and let's break this down. So there's falls and there's dynamic gauge stability. As yesterday during some drinks I already mentioned, I don't think that dynamic gauge stability is the only thing that quantifies if you're going to fall. Here's an example of Steve Rabinovich. He's doing research, has cameras everywhere in a nursing home, and there was an elderly guy and he fell. All of a sudden he just fell, and he didn't know what happened, and the nurses around didn't know what happened either. And normally he never fell. And they had the cameras around, so they took the material from the cameras and looked at that. And what happened? What was the case? He walked past somebody who was sitting in a wheelchair, and the guy in the wheelchair goes like this. So you can be as stable as you wish, but there's three factors, like I said. You can be as stable as you wish, but I think the perturbations you encounter during daily life are a big part of how much you're going to fall. If you're really stable but you encounter really large perturbations because you're walking in a mountain all day, well, most likely that you will fall more often. But after the perturbations, I think that there's a division you could make into stability concepts that's twofold. One is, I think, something which I would call the stability of the steady-state gait pattern. So how well are you able to cope with small perturbations, which if you walk in the street basically happen every step. Because every step is a little step up, step down, there's a gush of wind, somebody might bump into you lightly. And these don't really disturb your gait pattern. I mean, you can walk and you don't feel like you need to do something like that. So this is, I think, one part of stability that we can measure, and that is if you encounter the same perturbations, a greater stability of your gait pattern will lead to the fact that you fall less. And then I think there's a second thing, and that's the quality of recovery actions. So as you can see, I'm not really calling this stability anymore, because this is to me a different kind of action that you have to take. So you all of a sudden you hit some obstacle with your foot, and then you have to lift over it. It's probably highly dependent on how fast are your reflexes, how high are the torques you can generate, and that kind of stuff. Well, of course, I think all the three of them are important. If your steady-state gait pattern is not stable, you will get a small perturbation, next time another small perturbation, these will grow, and in the end you will have to use a recovery action, and if you assume that every once in a while you have to take a recovery action, this will fail, you will fall more. So I think that of the latter two, which we can measure easily, both are important. And I think that for my thesis I mostly looked into the stability of the steady-state gait pattern. And why? Well, it's actually really easy. This is not the slide I was expecting, but it doesn't matter. It's really easy because for the steady state gate pattern, you don't really need to perturb always. You can do it using internal perturbations, like sensory motor noise. At least there are some measures that state that they work like this, and I will come to that later if that really is the case. But you could also do it using external perturbations, like a push or a pull, that are not too big. For me, the advantage of not using an imposed perturbation is that you don't need to build a perturbation setup, and that your measures will be easily applicable in a clinical setting. I mean, the perturbation device we built, we had good technicians, but still cost half a year to build, and still doesn't work all the time as we wish it to work. So to give an overview of what I will be doing for the coming time, I will be talking about two measures of gate stability, and I think that the first one is linear response to an external perturbation, and I think that this one also captures part of something which you could call more the adequateness or the quality of the recovery action. So more the first thing I had as, or the last phase I had as gate stability, and the Lyapunov exponent. For each measure I will then discuss 4 things. First, the theoretical background. Okay, why do we use this measure and why should it work? Then applicability. So how easy is it to use and how well does it go? Then I will see how well does this measure do in a model. Because if it's theoretical, right, but it doesn't work in a model, like for instance a Floquet multiplier, well, I cannot say anything about the amount of steps still falling, so I'm not interested in it. And then how well does it correlate to real life notions of stability in human gait? So this is what I'll be doing for the coming, I don't know, depending on the questions coming, minutes. So let's start with a linear response. This is basically looking at how large a perturbation can you handle before you get knocked out of your steady state gait pattern. And for this we could use perturbations of increasing size, but that's not really what we want, because then we get subjects to fall and not really handy. And could also perturb subjects with a given force and then see who falls with this. Well, also it's a dichotomous variable, so you don't get a precise measure out of this. So you would want something more precise. In search for this, we built this machine, and it's around a treadmill, built around a treadmill, and there's ropes running here to the subject, and there's a pneumatic piston here pulling. So the rope is free running at first, and at a certain moment in time the rope gets blocked, the rope's on top there, it gets blocked, and the piston goes down, and you get a nice perturbation. These perturbations can be timed to a specific event in the gait cycle, so that you have really nice reproducible perturbations. Only thing is that this system is position control, so not force control. But we measure the forces that we get during the perturbation, so that you can say something about that. So we've been using this to deliver perturbations and see if we can develop some measure from this. So first thing we did was let's see how the distance towards a normal walking pattern behaves. So I plotted here the 3 velocity components of the trunk marker in a 3D state space. And this is the normal unperturbed walking pattern. As you can see, there's some variability there, which of course is to be expected. And then when we plot the perturbed trace, you can see that it follows nicely, and then there's the perturbation, and you'll have some distance away from the attractor, and you return towards it again. So here's another view of that. So on the top panel is the distance from the attractor, and on the lower panel you can see actually the little black arrow coming out here is the perturbation force. In this particular setting, the perturbation was not the perturbation to the side like this, but it was a perturbation basically just before right heel strike we would have a perturbation towards that side. And we did this, in this study was on the effects of arm swing, which I will show the results later on. So there were two conditions. In one condition, subjects swung the arm freely, and in the other one, they held them to the body. And this curve, which you then get, you can further parameterize. So this is the distance from the attractor. This was actually on a 6D state space, so not including only the linear velocities, but also the angular velocities. And this is perturbation onset, and then the little dot there is the heel strike just after the perturbation. So it's just before the heel strike is the perturbation. Of course, you could time this differently, and then this first point would look different. So then we measured the time to maximum distance was reached. Because the perturbation took the same time, this gives you an indication of how long are you moving away and how fast are you moving away, more importantly. And also the maximum distance from the attractor. So these combined give you an idea of how fast are you moving away from your attractor. So how fast. And then we looked at the exponential decay towards the attractor, back again from the maximum point. So this is basically, I would say this is already a recovery action. Although for this perturbation you could debate that it's still in the region of steady state gait pattern, but I would say you really see people, especially when they do it with the arms, you see them go like something different. It's not just continuing walking. And then there's the first recovery heel strike, and we also looked at how far are you away from the attractor at first recovery heel strike. Same idea again as previous one. If in subsequent strikes you get a perturbation again, you would want to be as close as possible again, because otherwise your gait pattern will get more and more and more perturbed. Did I miss one? Oh yeah, and this is the last one. The relaxation distance we used to check if for all conditions you basically go towards the same point again. So it could very well be that for walking without arm swing, the relaxation distance is further away anyway, because you have more natural variability. Because you'll never get exactly on the attractor because there is variability. We define the attractor, by the way, I should have said this. But no. We define the attractor as the average trajectory in state space of all strides of, I think, 100 unperturbed walking strides. So doing this for all the data of the in essence, to me this seems like a really plausible method to assess stability, and I think you can even, for the first phase, to see how fast are you walking away, in the second phase how fast are you going back. This it seems to me can give you an indication of both the steady state and the recovery, although it's maybe hard to separate those two using this particular experiment. If you do larger perturbations, I think you should be able. But like I said before, to me this is not so easy to use. I mean, it may look really nice, but this costs a lot of time to build. And it costs a lot of money to build, so you don't want clinicians to play around with this kind of stuff. Or if possible, if the money's there, this would be, perturbation experiments would always be my preferred choice, but it's rather not possible. So I did this is the modeling evidence that I have that such a measure can work. And this is not my own data, this is from Hobbel and Wisse. They did some simple modeling with a compass gait walker with arched feet, and they enlarged the arched feet, and they used the gait sensitivity norm, which is very much related to this measure, also a linear response measure, but it is it is not continuous measure, but step by step. So basically you measure the variability of a certain gate indicator for each step after a perturbation. And I did so, and I've been doing so as well, but not for this yet. And I compared it also with the actual disturbance rejection. So how well does this model do in terms of actual disturbance rejection? How many steps can it take till it falls for a certain amount of noise? And the noise was imposed by having the model walk over an uneven surface, like step down, step up each time. And you see that such a measure works really well. So that's good. Then for human data, and of course for human data it's always hard, and I haven't had a chance to do this with subjects who I expect to be unstable. So all I have is these data from this arm swing paper. But the results are interesting, and they learn us something which was in agreement with another paper, so in that sense we feel confident that it's really telling us something. So on the first panel is the perturbation force, so how much force does a given position-controlled perturbation generate. And you can see that this force is higher when you don't swing the arms. And then the maximum distance is the same, but the time to the maximum distance is longer, so implying that you're moving away slower. So this would to me suggest that your steady state gait pattern is actually more stable when you don't swing the arms. Which I kind of understand from the fact that, well, if you add mass to your upper body, probably it's going to be harder to perturb. You're going to need more force for the same position displacement. And it's in agreement with findings in the tripping experiments, which are done by Bruijn, who's in our department, where she did some, she measured the data and then did some simulations of what would happen if you cut off the arms at the instant of trip. And so, and then we looked at the exponential decay, and you can see that this is clearly faster when you have a normal arm swing. And also when you have a normal arm swing, your distance at the first heel strike is slower. So the arms are actually doing something in the sense that you're better able to place the next step somewhere in a good position and get yourself back to like your normal trajectory. So I've been looking at some animal stuff because we sent this to a biology journal, and actually I think that penguins are quite smart. They don't swing the arms except when they need it for a perturbation, and this is the way I would expect it to be optimal in a stability from a stability point of view. Although you would want to swing the arms for energy consumption. I mean, when you swing your arms, energy consumption is way lower during walking. So to do a short recap, I think that this is a really nice measure for theoretical reasons. I think for modeling studies there's also some proof that this works. Real life, well, we've only one study, but I think this study is in agreement with the rest of the literature. But although I would love to do some experiments with elderly, as a matter of fact, a colleague of mine is doing this now, where you also have the number of falls which the elderly experience during a year, which would be really good to do. And the only downside to me is that it's not so easy to use. You need the whole setup, and yeah, just takes time to build the setup, costs money. So. Then the second measure, which is can be measured from steady state gait, unperturbed gait. And I know a lot of people are skeptical about this measure, and I am myself as well. But I'm going to try to convince you, like I convinced myself, that, well, I'm skeptical, but I cannot find anything to, any evidence for my skepticality. So, cannot be anymore. So this is the largest Lyapunov exponent, or the maximum finite time Lyapunov exponent. Apart from all the mathematics behind it, which I won't go into too much, I will tell you shortly how to calculate it, what's actually done. So again, you measure your signals, and in this case we did time-delayed reconstruction of the attractor, but you could just as well do the same on build an attractor out of linear and angular velocities in 3D. And then you start looking at some point and you say, okay, what's the closest point to this? And I regard this as a small perturbation away from the other point. And if this is a small perturbation, of course, if the system is stable, these points should not move apart but grow together. And if the system is unstable, they will move apart. So actually, what you will find is that these points move apart, meaning that's unstable. So at least there's one unstable dimension in your attractor. Oh, I'm going too fast there. But the idea is that this instability will tell you something about how fast you're diverging in state space, and that this will tell you something about how stable you are, or rather unstable in that direction. So then you look at the slope on a log scale, and in most literature people look at two slopes: a short-term slope, which is usually from 0 to 1 stride or 0 to half a stride, and a long-term slope which is from 4 to 10 strides calculated. Then in one study I did, this was the first study I did on this measure. Because you need a lot of data for this measure, we were wondering, okay, how many data points do we actually need? So we recorded a lot of data, 20 minutes of walking, and we bootstrapped the data. So we picked out parts of first 30 strides, then 30 strides more each time, but of 30 strides, 1,000 episodes, and then up to 300 strides, and see what's the variance in the data. So how does the variance decrease? And of course it will decrease, because if you pick something that's 20 minutes long, you pick the same piece every time. But you can see here, these are the standard deviation for the long-term lambda S and lambda L. You can see that at least in the beginning there's a steeper decrease, which probably implies that your precision is really increasing. So we thought, well, at about 150 strides, you get the variability doesn't decrease that much anymore. What was more interesting though was not looking at the standard deviations, but by pure accident I plot a figure of the means, and this is what happens with the means when you use more strides. So when you use 30 strides or 300 strides, you will find a whole different result. Now this is very interesting, because this would mean that if I measure me from walking for 4 minutes, or I measure my grandma who walks with like this, really short steps, even if we walk at the same walking speed, I will find that my grandma is much more unstable. Even though this may not be the case. So from this study it became clear that it's very important to use the same number of strides for all your analysis. So also when you do test the different walking speeds and you measure 4 minutes at each walking speed, of course your higher walking speeds are going to contain more strides. And as a matter of fact, we did this study on walking speed. The results are not in this presentation, but I can tell you. Where walking speed was always reported that faster walking was likely less stable than slow walking. And this was also an explanation for why several patient groups were walking slowly. This was said not as this was to be an adaptation for the fact that they were unstable, so they would walk slow and then they would be more stable. And actually when we did the analysis in this way, taking the same amount of strides per speed level, we found that it may not be the case. It's probably faster walking is more stable, and which to me makes more sense. I'm Dutch, so I ride a bike a lot, and riding your bike slowly is really well. And I know from Dan Hobble, I talked with him. He did in his model. He also found that like the faster it walked, up to some point, the more stable it got. I don't know with your models and robots, but so this is one point we need to take care of when using these measures, that they're not very precise. They have quite some standard deviation, and you need to measure the same amount of data. However, they have a big advantage, and that is it working? Yeah, because they're built on a state-space description of the system. Any state-space description should lead to the same results, and this makes that you can also use as long as it contains the same information. So you could use an inertial sensors instead of an optoelectronic system. So you could measure position or accelerations and angular velocities in local coordinate frames instead of a global coordinate frame, for which you don't need a big camera system, and you can just, we use the sensor which you see on top, which is from Philips, and just slap it on somebody's back and measure, and it will should give you the same results. And indeed it did. Well, there was some noise from both measurement systems, of course, so you get some differences, but it worked fairly well. So we can just use a very small inertial sensor, and in fact colleagues of mine, they already used this idea and took one of those small inertial wireless sensors and one of the small treadmills which you can just bring along to a big fair for the elderly, and set up a measurement booth there and measured 130 patients or elderly subjects, also asking for a history of falls and those kind of things. So this really allows for larger scale projects where you can have a lot of people come into your improvised lab or even go to people's homes. And we're now also working on not only using this for treadmill walking, but we're trying to look at this I don't have the results of, but walking up and down a hallway, to see if we can do this. Although you need you need quite some strides. We thought, well, maybe you can do it with less strides and more episodes. So we have subjects walk up and down a hallway for 10 or 20 times and see how many times a stroll down the hallway is enough to find differences. So let's go a bit into the question. I guess is in all of your minds. So what does this tell me? Does this really tell me something about the chance of falling? And I think right now I'd have to answer yes, at least to some degree. This is a study by Su and Dingwell, and they had a confiscate walker walk on uneven terrain, point feet, and they increased the noise levels, and to see if the Lyapunov exponents also increased. So if they would increase, this would at least tell you something about the probability of falling. If they would not increase, it could still be that they qualify the stability of the model, of course, because the model itself doesn't change. And they basically found that the short-term Lyapunov exponent increases with increasing noise level, and the long-term that didn't really change. But this, I thought, well, this is all nice and everything, but in their model, as I said, nothing changes in the model. It's the same model, so the basin of attraction of the model is the same, and of course if you add more noise, it's more likely to fall. So, okay. So I took the idea of Hobble and Wisse, which I presented earlier, and took the model with RTV, and then did the same thing. So it's on one noise level, and I looked at this is not only changing the arc of the feet, but also at the same time changing the slope to keep step length equal. I did the other simulation as well, but I don't have a figure of that yet. But as you can see, there is too much measures in here. But so first, the black solid line is the gauge sensitivity norm, which correlates well with actual chance of falling. That's been shown in that paper. I didn't calculate it yet. I'm working very much on this. This was in the train. So the black line is basically chance of falling, probability of falling. Then the first one that goes very well with it is the short-term Lyapunov exponent, maximum Lyapunov exponent, and it correlates very well. And this is the one thing. These are all 1 over gauge sensitivity norm, 1 over Lyapunov exponent, and 1 over maximum Floquet multiplier. And this is an important thing, as we see in the next slide. And I also plotted here the Floquet multiplier, but as you can see, well, long-term Lyapunov exponent and Floquet multiplier, they're basically not doing so well in terms of predicting the probability of falling. So on the right side is just a graph to give you an idea of the correspondence. Well, looks quite nice. What struck me though was when playing around with this is that when you plot the gauge sensitivity norm against probability of falling, you get something like this. And I can tell you that if you plot 1 over gauge sensitivity norm against the probability of falling, you get a straight line. So, given the fact that here we also get a straight line, probably the correct measure to look at would be 1 over the short-term Lyapunov exponent. And I'm wondering, is this also the case for variability measures? Because, of course, if you have a small amount of variability, a little increase will do a lot to your probability of falling. But if you're over some boundary of variability, it doesn't matter anymore. And still, all this variability literature, I did myself as well, so I'm not blaming anybody, but all the variability literature is talking about just variability. And I think that the correct way to assess it, to look at these things, would be 1 over variability. And this would give you a better idea than just variability. But this is, well, it's in progress. And yeah, I'm really interested to see what we get more out of this. But so this is the model data I have. So from the model I would have to say at this moment, well, for a model at least, it gives you an indication of the probability of falling. And then for humans, because this was my scheme, right? First show what is done, how easy it is to use the model, and then for humans. Well, for humans. There's quite some studies that they can discriminate between elderly and younger subjects, between patient groups. But walking speed was not controlled in a lot of these, so you don't know whether you're looking at effects of walking speed or the effects of a pathology or aging. And different numbers of strides were analyzed, so it's closely related to the first one, of course, but not necessarily the same. We did a study ourselves on patients with knee osteoarthritis, and we could not find any relationship between the number of falls experienced and the Lyapunov exponents. However, we did find a relationship between measures of variability and the amount of falls experienced, although it was not so true. But so we did a study in which we said, okay, well, the best thing would of course be to make subjects unstable, not to take 2 different groups of subjects, because you never know what's different between them. We want to have one group of subjects in a stable condition and an unstable condition. So we had a master's student doing this project, and she came up with, we give them vodka. And we went, well, it would have been nice. But the ethical committee would then ask you to have them inside as long as they still have alcohol in the blood. So you would have to organize a movie night or something and then measure everyone. You cannot have subjects walk out of the building if they're drunk, unless they get drunk by themselves. So then we come up with this thing, this galvanic vestibular stimulation. It's basically 2 electrodes which you slap behind the ears, and it passes a current through your galvanic organs, and it's really funny. This is a Japanese movie, and of course they know how to do it, so they made a gaming control of it. And this guy is basically controlling where she's going. I think on the website it said something that they wanted to use this in together with virtual reality helmets to make gaming experiences more real. So. So we did something similar, but not quite as like this. We had a galvanic visual stimulation system, and we had a combination of 5 sinuses, which were a non-integer combination, so you get a pseudo-random signal. So you never know what kind of signal you're going to get, so you cannot adjust to it or whatever. And it was very slight, so if you put it on, you'd feel slightly dizzy, but not very dizzy. I've had it on with high currents as well, and then it feels like, well, basically, as soon as they turn it on, your eyes go, and you move the other way. It's really funny. We had subjects walk in a normal condition, just on a treadmill, and then we had them walk with galvanic vestibular stimulation. And just to show you that it wasn't really this much what we did. This is a movie of a subject walking with galvanic vestibular stimulation. Well, he's walking slow, so he's wandering around anyway. You can see some steps where you think, well, maybe this is caused by the galvanic vestibular stimulation, but not too much. So by doing this, we made sure that they missed some sensory information, which would make them less unstable, or if they were still relying on it, depending on which kind of sensory integration scheme you're expecting, they were still relying on it, and they had faulty information, which would also make them more unstable. Interestingly, we could see this with the short-term Lyapunov exponents, not with the long-term again. Actually, results on the long term were in the opposite direction. So now we have a controlled experiment where we can also say, well, it seems to work. It shows the same pattern as what we expect. Also, and I did not include the slide here, during the arm swing experiment of the steady-state gate trials there, we also measured the Lyapunov exponents, and for the short-term Lyapunov exponents we found basically the same thing as for the initial response to the perturbation, that when you walk with the arms next to the body, they would indicate that you're more stable as opposed to when you're swinging the arms free. So all in all, this is something which has gone wrong, because these green thingies should be there all in all to complete the scheme. I think that it should work, although they're measuring instability and we're looking at stability, which might be a bit weird, but easy to use, real life. I think there is ever more evidence also from some other papers and conferences I've seen so far, and in the model they also seem to hold up pretty well. Still, they only assess the stability of the steady-state gate pattern, and even local stability, well, although they correlate with probability of falling, which would make them not so local stability, you might say, and not how well you're able to recover after this perturbation. And you'd really like to see that as well, actually. I mean, if you keep the scheme of 3 things which are important, you'd want to measure the 3. But with this one, you might have at least one of the 3 components covered, and it's for clinical use. I think it would be perfectly feasible for therapists to use this measure, if there is, of course, a database with a normative database, all that kind of stuff. So, but yeah, because we measure only this one thing, is not quite sure yet of if it is really relating to probability of falling, and like I said, we should look at how it relates to number of falls also. well, the first part was actually from a previous presentation, should have left the time. But we have some data already where we're doing this right now. I measured hip replacement patients because my original PhD was going to be about hip replacement. And we measured them before the operation, a month after, 6 months after, 12 months after, and see how they recover. And we have perturbation measures and also steady state gait walking. So we can do this. And we also have questionnaires on self-perceived stability, fear of falling, and number of falls. And this study, last one, which I'm going to present, was presented some months ago. And that this was actually at the fair for the elderly, like I told you. So they had this big poster, and the elderly would come there. It's all in Dutch, so you can't read it. But and the data was, the guy who was doing this, he came into my room like just the day before I left here, and telling me that he found a correlation between the amount of falls subjects experienced. So this was over 130 elderly, and the Lyapunov exponent of 0.3, which was highly significant, which would indicate that, well, it gives you at least an indication of the probability of falling, and this is what I want to know. So I think that studies like this are really good for future work, and then in combination with maybe also assessing the perturbation, the recovery after perturbation, and what would be really interesting then is to see if you can find some way of measuring the amount of perturbations people encounter during daily life. I think if you have those three factors, you should come to a very good correlation to actual number of falls experienced by such. And this is basically what I wanted to do. Thank you. I need to thank some people, my supervisors for my PhD project, Anno Meijer, Peter Beek, Jan van Dier, and some other people who help with galvanic vestibular stimulation, the inertial sensors and the modeling work, because I couldn't do it without